So previously we had talked about how we can test if a language is empty or not. In addition, we've also talked about a bunch of closure properties. For example, we talked about the regular operators. We also talked about intersection, complement, and also reversal. So I'm going to now talk about two more kinds of properties you might test. One is going to be very common for us. We've talked about this many times. We've framed decision problems like this. Is testing membership. So if I want to know if a string is in a language or not, this is actually how we introduced the idea of thinking about a language as a decision problem. And this is one way you might think about this. So given a string W, is W in the language? Very, very interesting question. So let's address this for regular languages. So suppose that L is regular. So we're going to talk about it in this context. We've talked about this many times, so I'm going to go a little fast on this. But I'm going to talk more about complexity, namely, and the process. So suppose that L was described by a finite automaton. So what you do is you would simulate, or just run it, right? You simulate the finite automaton processing string W. So processing W. So if the automaton ends in a final state, what does that mean? It means it accepts, right? Which means it's a part of the language, which you would return yes, right? Otherwise, it's no, right? Otherwise, you read this, the automaton read W and now is in a non-final state, right? So otherwise, answer no. Okay. Now, suppose that the length of the string was n. When the length of W is equal to n, and a DFA is represented, I must stress that the main ideas here are going to be generally true for finite automata, but other kinds as well. But I'm just going to restrict this just to DFA. And a DFA is represented as a two-dimensional array, which is, of course, its transition table, which we talked way back. This is one natural way to implement a DFA in terms of how you represent it as a transition table. Each transition takes constant time, and the test overall takes big O of n time, where n, of course, is the length of the input. So this is quite natural, right? Because we read each symbol one after the other, right? And so we transition to another state, but notice that the execution is completely dependent on the length of the string. Now, you might ask, okay, suppose it's a regular expression instead. Now, this is just one way of going about it. It's going to be very similar to what I said previously. So you can always convert the regular expression to a finite automaton. Such as an epsilon FA using Thompson's construction, to a finite automaton. Then perform the above. So remember, this discussion applies to just any finite automaton. Just I wanted to keep it simple for us. Now, this was a piece of cake, right? We've talked about this for many, many, many lectures. We've talked about everything has always been in the context of testing if something's in a language or not in terms of the strings, right? Well, let's ask a different question. If we are given two regular languages, suppose we call them L1 and L2. How do we test if L1 is equal to L2? Now you might be looking at this saying, Dan, why should I care about if I give you two regular languages? How do I know that they're equal or not? Well, think about it this way. You have two people, person A, person B. Person A comes up with a DFA. Person B comes up with a regular expression. And I would like to know, is person A's DFA is going to be describing the same language as person B's regular expression? If you see it like that, now it's more of a question of are we actually seeing that these things are in fact, are they actually the same language that we're describing? So I'm going to present this as a theorem. So here's a theorem. So I'm going to use some set theoretic fun here to go about this. So I'll let you think about the steps of this proof. But I must assure you, the way I'm going to present it to you is going to use set theoretic operations. So I just warn you that that the way this proof is going to play out is more about the existence of a DFA as opposed to me showing you how to build the DFA. But it'll be implicit in how I define it, okay? And that part I'll let you think about. So given two languages, L1 and L2, there exists an algorithm to determine whether or not L1 is equal to L2. So let's prove this. Now, I'm going to come up with a rather, I would argue, is a little bit of a, at first it's going to look a little strange, but I'm going to design a new language that will be regular, and it's going to have a very nice property to it that we can use, and it'll actually come back to the question about determining if a language is empty or not. So by the way I'm going to come up with the language, I'm going to allow it so that it becomes really a test if the language is that I come up with is empty or not. If it's empty or not, it'll tell us if they're equal or not, i.e. L1, L2. So consider, so at first it's going to come out, it's going to look a little strange at first, but if you think about it from a set theoretic standpoint, it's not too terribly scary looking. So imagine I have L1 and L2, so I'm going to consider L3, so I'm going to build L3 out of the following operations, which we all know will yield a regular language. So we're going to consider L1 intersect L2 bar union L1 bar intersect L2. Now, we're going to see why I picked L3 like this. I got a little excited there. So, since L3 is regular, and I'll leave this as an exercise for you to prove using the similar kind of arguments we've seen when we built expressions like this using set operations. Since L3 is regular, there exists a DFA. There exists a DFA that recognizes L3. Right? Now, you might ask, Dan, what's the algorithm going to look like? Well, I'm going to come up with this DFA, right? So I have the DFA. Then I'm going to now test for emptiness on L3. Now, if you're looking very carefully at this, you might notice that I'm actually describing something that looks like set difference. So I'll get to that in a moment. So check whether L3 is empty or not. Using the reachability process described previously. What you could actually show is that L3 is empty. It's the empty language if and only if L1 is equal to L2. So now what I want to do is I want to convince you that this is in fact the case. So I'm going to make an argument showing you that this two-directional connection here is existent. So I'm going to prove both directions separately. So let's watch this carefully. So I'm going to actually prove them over here, just for the sake of brevity. That I don't want to cram everything on over here. Let's prove this claim. Let's prove the part that says if L3 is empty, then L1 is equal to L2. So we're going to prove that part first. So if L3 is in fact empty, then what does that mean by definition? Then it has to be that both, because remember, it's connected by a union, right? So we have the first part and the second part, then there's a union in between, right? So that means that then both L1 intersect L2 complement, which this, if you look carefully at this, is actually just set difference. This has to be equal to the empty set. But what does that mean? Well, this is another way of me saying that L1 is actually a subset of L2. Why? Well, think about it. That means that for this to be empty means that I was able to take out everything using L2. Meaning that L1 has to have at least whatever's in L2 to do that. That's at least one part of this. Both this and L1 bar intersect L2, which if you look at this carefully, this is another way of me writing the following. It's just really L2, because remember, I could just go like that. It's L2 set minus L1 is empty, which this implies that L2 is a subset of L1 are true. So both of these have to be true. Actually, let me get rid of the both, because that's just too much. There's too much both in this proof. It's true. So, what does that mean then? So for those that are acquainted with sets, I've just said to you, if it's empty, then L1 is a subset of L2. But that also means that that L2 is a subset of L1. That means everything that would have been in L1 has to be within at least L2, and everything in L2 is at least within L1. But what does that mean? They're equal by definition. That's what set equality means. So that's what it means for two sets to be equal. by the definition of set equality, L1 is equal to L2. So if L3 is empty, then L1 is equal to L2. Now let's prove the other direction. So this direction is saying if L1 is equal to L2, then L3 has to be empty. So if L1 is equal to L2, then, now this one's going to be, I like this part of the proof, it's fun. Then L3 is equal to L1 intersect L2 complement union L1 complement intersect L2, right? But what does it say? If L1 is equal to L2, what happens here and what happens here? So if they're equal to each other, well, L1 is L2, right? So that means that if I may as well just put L1 right here. But that's L1 complement. What happens then? So let's look at the picture here. So imagine I have L1, and L1 is equal to L2. So L1 is equal to L2. That's a circle right here. Out here, outside of this, that's L1 complement. And remember, intersection means take the elements that are in common, right? Are there any elements in common among L1 and the complement of L1? No, there's none, right? All of these are out here. All of these are within here. But there's none in common. So this is the empty set. So it's the empty set or empty language union. By the same reasoning, you could say the same thing here. Which this is equal to the empty set. It's empty set or empty language union empty language. It's just an empty language, completing the proof. Thus, I've come up with a way to test if L1 and L2, given that they're regular, that there exists an algorithm for testing equality of two languages. Miss Kitty, what do you think of that? She thought it was pretty neat.